Let's take a look at exponential growth and decay models. So exponential growth, we use this equation right here, either y or f of t, where we have our principal value. This is our initial. R is the rate at which our population is changing, and then t is the time. With growth, our initial value is added with our rate, while with decay, we subtract the rate. And again, f of t for our decay. So they're almost identical, just one's a plus, one is a minus. So let's take a look at one of our problems here. So a house originally cost $20,000 in 1950, and that value has increased 5% a year all the way to 1995. What is the value of the house in 1995? So what I like to do with all these problems is go through the four major pieces of our formula and see if what I know, so I know what I'm looking for. It originally cost $20,000, so that's our initial amount P. Our rate, 5%, we're going to write it as a decimal, 0.05. Then the time from 1950 to 1995 is 45 years, so we want to figure out the new cost right here. So if I set up our formula, we know that it's going to be a growth model because it's increasing. 20,000, 1 plus 0.05 to the 45th power. Can grab our calculator. As it loads for me. All right, clear out what we were doing beforehand. And I'm going to take 20,000, 1 plus 0.05, and I'm going to raise it to the 45th power. So after 45 years, that $20,000 house is worth $179,716. 179,716. 179,700. Good. Maybe we have a decay model. So we have a powerful computer purchased for $2,000. Maybe it's a MacBook. But on average, it loses 20% of its value each year. How much will it be worth in 4 years from now? So again, if I have P, R, T, and F of T, we know the initial amount, 2,000. We know the rate, 0.2. We know the time. So once again, we're looking for that final value. F of T, P, 1 minus R. It's a growth because it's losing value. Type that into our calculator. 2,000, 1 minus 0.2 to the 4th power. Whoops, guess I didn't hit the caret. And so after 4 years of owning that computer, it's only worth a measly $819.20. That's all it takes, $4, and it's already lost more than half of its value. So let's say we actually have to figure out something other than f of t. So percentages, unfortunately, don't work perfectly forward and backward. So we can't set up the problem where 35 is now the principal and we use the 4%. And so in this case, since it's increasing, it's a growth, we can't set up a decay model to go backwards in time. The percentages don't work perfectly that way. So we're going to set up the original problem and work our way backwards. So at your grandfather's favorite restaurant, it costs $25.25. That price has been increasing 4% every year. We want to know what was the price 35 years ago. So the equation that we want to set up, f of t, p1 plus r to the t. When we plug in our numbers, we know that the final price is $25.25. We don't know the initial. We know the rate and we know the time. Unfortunately, we can't just rewrite this equation and go, all right, well, that's a growth. Why don't we just work backwards and set up this problem? F of t equals 25.25, but the price needs to decline for 35 years at 4%. Fortunately, these two answers do not yield the same number that we want. Like if we were to try it in our calculator, there's my calculator, 25.25, whoops, and we ask it to go 1 minus 0.0, of course, I'm just misclicking just enough to be annoying, for 35 years, $6.05. Let's see if we get the same thing. I might be surprised about that. So according to this model, it cost $6 when he originally went to the store. So if we set up this one, we're going to solve for P. So we've set up our equation. We're going to solve for P. So we're going to take 1 plus 0.04 to the 35th power. So I'm going to grab my calculator. 1.04 to the 35th power gives me 3.95. That number is multiplying our initial value P. We're going to divide both sides by 3.95. And so 25.25 divided by 3.95 gives us 6.39, so 6.4 equals P. So originally his favorite meal cost $6.40. Very close to what happens if we set up the equation the other way. It got close with $6.05, but they're not the same. So we have to set it up the long way and solve for P this way. So maybe we have a population of spiders. It's growing with exponential growth. If the population of spiders started with 42, and after 157 minutes there are 941 spiders, we want to know what is the growth rate. So we know that it's exponential growth. So we're going to set up our exponential growth equation. They started with 42. We don't know the rate. 157 minutes. We now have 941 spiders. We plug all of that in. 941, 42 for P, 1 plus R, and then T is 157. We're going to work our way backwards undoing all of these numbers. The first number we're going to undo is this 42. It's multiplying, so we're going to divide. 941 divided by 42 gives us 22.4. What we're left with is this that's being raised to the 157th power. To undo an exponential power, we have to take the root of that same power. So if I had x squared, we would take the square root. If I have x to the fifth, I take the fifth root. Lucky for us, we don't have to worry about this button on a calculator at all. It turns out that square root can be written as something to the 1/2 power. The fifth root can be written as something to the 1/5 power. So we're going to take this number, 22.4, and we're going to raise it to the 157th power. So literally we're going to take 22.4, we're going to raise it to the 1 divided by 157th power. That gives us this. (1.02). We subtract 1 from both sides, and so these spiders are growing at a 2% rate. So again, on your calculator, if you want to take something and you want to take the square root, so you could take 36, and if you were to square root it, you could type into the calculator 36 to the 1/2 power, and both those answers would be 6.